All right. Start a new page here. Okay. So what we're doing today is we're working on solubility product equilibriums. All right, solubility product is where the SP comes from on KSP. Okay, so immediately if you see KSP, you're doing what we're going to start doing today. All right, solubility product equilibriums kind of blows away some of what we've done with solubility rules. Okay, do you guys remember your solubility rules? You need your solubility rules. Okay, your life will be a lot easier if you have your solubility rules memorized, all right? Especially the ones that don't have any exceptions. For instance, all group 1 metals are soluble, acetates are soluble, nitrates are soluble, and your perchlorates and chlorates are always soluble, okay? If you can have those memorized, that'll get you a little bit taken care of, and then you just need to work towards the other ones. Is everybody with me there? Solubility rules will make your life a lot easier, okay? Here's the deal. We've gone on the assumption that if I write something like silver chloride and I put it as S, that means it's insoluble, right? What it actually means is that it's very, 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 very slightly soluble. Okay? So don't completely change what you're thinking here. Just understand that if I were to take some silver chloride and I were to put it into water, it's going to stay as a precipitate. But on the particulate level, there's a very, very, very small amount of silver ions or chloride ions that will actually go into solution. Is everybody with me there? Okay. So first thing you got to be able to do when we start solubility product equilibriums or solubility equilibriums is you have to be able to write the chemical reaction that we're looking at. All right. So, you know, I call them ice tables. In the books, they call them rice tables because they want to make sure you don't forget to write the reaction first. Is everybody with me there? So what you have to be able to do is you have to be able to write your dissociation equation is what these are called. Okay? Because what we're talking about dissociating an ionic compound, okay? Now, when we dissociate an ionic compound, simply what are we doing? Breaking it apart, breaking it into a positive ion and a negative ion. Is everybody with me there? So we're going to write it like this. You have to make sure that what you write for your products, I'm going to put the symbols in here. You can leave those off. Okay, just make sure you know what you're looking at. Make sure that you write them as ions, guys. If you leave the charges off, they're not ions, and you will not get points for it, okay? That's one of those ticky-tack things that, although it seems kind of ticky-tack, it's absolutely wrong if you don't write it as an ion, okay? If you write just Ag there, that indicates silver metal, like there's a quarter in there, a pre-60s quarter. Is everybody with me there? As opposed to silver ions that are in solution. All right, is everybody with me? Okay. Once you figure out that the dissociation equation looks like that, then what we can do is we can write an equilibrium expression for this. The equilibrium expressions for KSP are always really, really simple because none of them have a denominator, ever. Okay? Because the only thing that's on the left-hand side in your reactants is a solid. Because we're doing solubility of a solid. Is everybody with me there? And so this guy here is always going to be a solid. The coefficient in front of it is always going to be a 1. Everybody with me there? So if we were going to do this guy here, KSP would be equal to the concentration of silver ion times concentration of chloride ion. The equilibrium expressions are super simple, all right? And the reason why they're simple is because All the rules for equilibrium expressions we've already talked about. You never put a pure solid or a pure liquid into an equilibrium expression, right? Okay?
And can Ksp still be concentration or pressure?
No gases,
Okay.
okay? So, yeah. So when you're doing an SP, that's why it's SP. That's why it's not KFC or KFP. It's KSP. And the good news is that'll help you see right away what kind of problem you're working.
Yeah.
If you're reading the prompt and you see a KSP, you know you're doing a problem like this. Okay? Okay, everybody good so far? All right, now we're going to take a little detour here real quick. Okay, we have something called molar solubility. Okay, molar solubility is an add-on to a really, really easy term called solubility. Okay, all compounds that are soluble or slightly soluble have a known solubility. Okay, and what I mean by that is I can go look up the solubility of sodium chloride in water. Okay, and what that's going to tell me, that's going to tell me how many grams of sodium chloride can I put into a given, like 1 liter of water. Everybody with me there? If I get above that, what am I going to have? I have solid left on the bottom. Okay, you guys have all done this. If your parents let you make your own Kool-Aid out of the pre-mixed deals that got sugar in it already, you guys have all done this. You put so much in there that there's always some sugar at the bottom. Okay, you just exceeded the solubility of that solid. Is everybody with me there? You dissolved as much in there as you could possibly get, and there's some left at the bottom. Okay, you made what's called a saturated solution. Okay, your solution is holding as much solute as it can hold for that amount of water. Does that make sense? Okay, that's what we call the solubility. All right, typically it's done in grams per liter, but the molar solubility is done in moles per liter, like a concentration. All right, why would it be done in grams per liter? Because that's how we mass things. Okay, so it's convenient. If I were looking up the solubility of sodium chloride in water, I'd want to get a number in grams so I can go over there and pull a balance out and make a saturated solution. Is everybody with me there? Okay. So the molar solubility is the maximum number of moles of something per liter of solution. It's just the amount that it can hold. It's the amount that solution can hold. When you reach that, you've got a saturated solution. If you're under that, what do you have? Think back to last year.
A mixture. I took a shot.
You do have a mixture. You have a solution. A solution is just a homogeneous mixture, right? Okay. So if you're at the max molar solubility or above it, you're at a saturated solution. Okay. You'll have solid left at the bottom. Is everybody with me there? Okay. If you're below that, you're at what we call an unsaturated solution. And then if you manipulate things to make it hold more than it should, it's called a supersaturated solution. Okay, so that's when we make rock candy. So like you put sugar into water and you heat it up, because when you heat it up, the molar solubility of most solids goes up. Okay, and so if we have hot water, we can get more sugar to dissolve in it than we do cold water. And then what we do is we take that mixture we just made and we let it cool down. So now all of a sudden we have more sugar dissolved in it than it should be able to hold at that temperature. That's what we call supersaturated. And then what's going to happen is when you disturb it some way, all of that solid comes out in the form of crystals, and that's how they make rock candy. Okay, everybody good? Okay, here's the deal. Molar solubility on these problems is X. All right, and so what I'm talking about is when we do, so for instance, we got the silver chloride solid goes to silver plus chloride, right? So initially, what value of silver do I have? 0. What value of chloride do I have? It's also 0. This doesn't matter, it's a solid. Is everybody with me there? What's my change going to be? This doesn't matter. This will be a plus x. This will be a plus x. Everybody with me? At equilibrium, this doesn't matter. I have x and I have x. The Ksp for silver chloride, I don't remember, but hold on. 1.6 times 10 to the negative 10. Okay, so if the Ksp is equal to 1.6 times 10 to the negative 10, we wrote the expression right here. Okay, so I can plug those in. Everybody with me? Is equal to x squared. Then x is basically equal to the square root of 1.6 times 10 to the negative 10. Y'all with me? So x on this is equal to 1. Okay. Here's what we found. We found two things. First thing we found is that the molar solubility of silver chloride is that. Everybody good? Two other things we found is that at equilibrium, what's the concentration of my silver ion? It's X. Right here, right? So the concentration of my silver ion is 1.3 times 10 to the negative 5th at equilibrium. And so is the concentration of my chloride ion. Is everybody with me there? Now, next question. If I have a saturated solution of silver chloride, what's the concentration of silver ion in that solution? Saturation or saturated solution is code. Saturated solution is at equilibrium. Write that down, circle it, box it, put a star next to it. If they tell you a solution is saturated, it's at equilibrium. Okay, that's code. Saturated equals equilibrium. So if they ask you at equilibrium, what's the concentration? Then, or sorry, when the solution is saturated, what's the concentration? They're talking about at equilibrium. Everybody got me there? Okay, it's nothing new. They just use a different term. They use saturated instead of saying at equilibrium. Does everybody got me? Anybody got any questions? Okay, now, what happens if I have a compound like that, BiS2, which has a Ksp of that. Bi2S3. So it's just bismuth sulfide. Okay? If I have that compound right there, what's the molar solubility of that compound? Now, here's the deal. I said, what's the molar solubility? What am I really asking for? What's X? Okay? And so what we need to do, we're going to start this by writing a dissociation equation. Okay? Again, big words, meaning split your ions up. That's it. Right? Okay? So bismuth 3+, and there's 2 of those, plus sulfide, which is 2-, and there's 3 of those. Yeah, that's fine. All right, everybody with me? Okay. So this guy doesn't matter. Initially, I have 0 of this, I have 0 of this. My change is going to be what? Plus what? Plus what? 2x. Remember, your change is your stoichiometry. So the coefficient matters, okay? And it also matters that you have it balanced correctly. So you have to pay attention to what you're doing, okay? So then the sulfide is going to be what? Correct. Okay? Then at equilibrium, this guy is 2x, this guy is 3x. All right. Always write your expression. So this one is concentration of bismuth ion squared times the concentration of the sulfide ion cubed. So 1.1 times 10 to the negative 73rd, which is really, 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 really small. All right, is going to be equal to 2x squared. Everybody with me? All I'm doing is plugging these values into my equilibrium expression now. Times 3x cubed. Now, I've told you this before, okay, and this hasn't changed. It's extremely easy to forget that this is 2x that has to be squared, okay? It's extremely easy to just write 2x squared and then roll with that number. Is everybody with me there? But what I'm saying is this is actually 4x squared because we have to do the math. Everybody got me there? And then this is going to be what? 27x cubed because it's cubed. Everybody with me? Okay. So 1.1 times 10 to the negative 73rd is equal to 4x squared times 27x cubed. 1.1 times 10 to the negative 73rd is equal to 108 x to the 5th. Okay, just 4 times 27, right? So then we're going to take 1.1 to the negative 73rd divided by 108. Get something that's pretty much uglier. 1.0 times 10 to the negative 75th is equal to x to the 5th. And you just take the 5th root. Calculator. So for x, I get okay. So on this one, my molar solubility is 1.0 times 10 to the negative 15. And don't leave it naked. Put a unit on it. Okay? 2 things. We're not searching for x. We're searching for the molar solubility, which just happens to be the same number as x. Everybody got me there? Okay, so label it and put a unit on it. All right? Everybody with me so far? Okay, now, here's the deal. in a saturated solution, what's the concentration of bismuth ion? At equilibrium, which means it's saturated, it'd be 2x. You with me? I just pushed out the calculator. I really did.
I do.
At least I'm not alone. Okay, because here are your equilibrium values. Everybody see that? I've got for my bismuth at equilibrium, which means saturated, it's 2x. Okay, the reason why is because that compound has a molar solubility of 1.0 times 10 to the negative 15th. But when it dissociates, how many bismuth ions are coming off? 2. Okay, when bismuth sulfide breaks up, 2 bismuth come off, and then 3 sulfides come off. Has everybody got me there? Okay, so the sulfide ion concentration, when it's saturated, would just be 3 times that. All right, with me? So if you have an ion, that's 1-to-1 with your compound, the molar solubility is the concentration of that ion at equilibrium, because it's just X. All right? If it's anything other than X, you just multiply the molar solubility by that. It's just like doing stoichiometry. Okay, we good?